We have this plain stress. First, we need to list the stress components on the element. We have sigma x equals plus 80, sigma y equals 0, and tau xy is minus 50. All units are in megapascal. Remember that shear stress is negative because tau xy acting on x face is in the negative y direction. You can also do the same argument for the other shear stress component acting on other three faces of the element. Clearly, all are minus 50. To start drawing the Mohr's circle, we draw the sigma and tau axes first. Then, from the x face, we locate sigma x equals plus 80 along the sigma axis. On the x face of the element, the shear stresses tend to rotate the element clockwise, so we go 50 units in upwards direction. This will locate point A on the circle. On the element's y face, we have sigma y equals 0, and the shear stresses of 50 megapascal tends to rotate the element counterclockwise. So we go 50 in downwards direction to locate point B. The line AB forms the diameter of the circle since both points A and B are the same vertical distance, 50, from the sigma axis. The intersection of a line AB with sigma axis is the center of the circle, point C, which has the sigma value of the average of sigma x and sigma y, so it'll be at 40. And now we can draw the circle. From triangle ACD, we can find the circle's radius, which is the hypotenuse of this triangle. So the circle's radius is 64. Now, let's find the principal stresses. The intersection of the circle with the sigma axis locates the principal normal stresses, sigma 1 and sigma 2. Sigma 1 is OC plus radius, which will be 40 plus 64 equals 104. And sigma 2 is OC minus radius, which will be 40 minus 64 equals negative 24. The angle 2 phi sub p, which is the angle from the x-axis to sigma 1 in clockwise direction, is calculated by tangent inverse of 50 over 40, which is 51.3 degrees. You can see the sigma 1 and sigma 2, which are respectively 104 and negative 24 megapascals. The angle phi p on the stress element must be measured in the same direction as is the angle 2 phi p on the Mohr's circle, but only half of it. So from x, we measure 25.7 degrees, which is half of 51.3 degrees. Clockwise, to locate the sigma 1 axis, the sigma 2 axis is 90 degrees from the sigma 1 axis as shown. Note that there are no shear stresses on this element. Now, let's find the principal shear stresses. They occur at points E and F with values equal to the plus minus of the circle's radius, so minus plus 64. It's also clear that point E is 38.7 degrees counterclockwise from point A on Mohr's circle, which is our principal shear stress angle. In order to draw the stress element associated with principal shear stresses, we need to draw an element oriented 19.3 degrees, half of 38.7, counterclockwise from x. We have the shear stresses at 64 megapascals, and the normal stresses corresponding to these principal shear stresses are each 40 megapascals as shown. Please let me know if you have any questions.